Swayam Prabha. Digital India. Educated India.
Welcome to today class of nonlinear vibration. So, previous classes we are starting with the applications of nonlinear vibrating systems, and we have already covered the flexible nonlinear systems. Particularly we have taken a base excited cantilever beam, and in that cantilever beam we have attached one mass at arbitrary position which gives rise to internal resonance conditions. Also we have considered three different type of beams, where we have taken this elastic beam, viscoelastic beam and elastomagnetic beam, and further we have applied piezoelectric pads to this cantilever type of beam and converted that thing to an energy harvester. So, we have studied all these cases where we have seen these nonlinear systems gives rise to different stability and bifurcations. So, particularly we are consider the fixed point response, stability and bifurcation of the fixed point response, where we observed this pitchfork type of bifurcation, saddle node type of bifurcation and also hop type of bifurcation. In addition to that, so we have seen this periodic, quasi-periodic and chaotic responses. So, this periodic response also we have seen, so it may be single periodic, two periodic, or it may give rise to period doubling route to chaos also. Quasi periodic route to chaos also we have observed, and this torus breakdown route to chaos and several type of crises are also we have observed in the previous classes. Now, next two classes we are going to study regarding this nonlinear vibration observer, because as there is vibration in the system, so we must know how we have to observe the vibration, or how we have to contain the vibration, or how you have to control this vibration. To observe the vibration, so we must know what is the principle of vibration observer. So, how it is different from vibration isolation. So, already we know what is vibration isolation. That means, so for a linear system we can isolate the vibration of the system. So, by operating it at a frequency very away from the natural frequency of the system. Similarly, in case of nonlinear systems, so as the resonance is not occurring at a fixed point, but at a range of frequencies. So, in that case, so we must have to develop some mechanism to control this vibration or to isolate this vibration causing in a system. Similarly, this principle of vibration observer in linear case we know. So, we know that by adding a secondary system to the primary system, primary vibrating system, so we can control or we can observe the vibration of the primary system. So, it will happen if the excitation frequency of the primary system is equal to root over K2 by M2, where K2 is the stiffness of the spring system we have attached to the secondary mass, and the mass in the secondary system is M2. We will see in case of nonlinear systems how we can observe this vibration, or whether this tuned mass damper vibration tuned mass observer is applicable to a nonlinear systems or not. So, next two classes we are going to study on this vibration observer, and later we will see some examples of electromechanical systems and some other systems in the application of these nonlinear vibrating systems. Vibration observer, so already we know that there are several engineering structure and machines. So, there will be vibration due to unbalanced force. So, this we must develop some vibration reduction methods. So, one is the vibration isolation and other one is the vibration observer. So, in case of vibration isolation, we can do this force isolation or base isolation. Similarly, in case of this vibration observer, so we can have the passive vibration observer or semi active vibration observer, or we can go for this active vibration observer. This shows a schematic diagram of a active vibration observer, where we have this primary system. So, this primary system, this is the passive system, passive spring and damper are attached to the system. So, now we can put a controller, we can put the actuator, sensors and controller. So, sensors will sense the vibration, and then we have to put a actuator which will actively, so which will be actively controlled. The motion of the actuator can be controlled in such way that it will achieve the absorption of the primary system, absorption of the vibration of the primary system. We can have the hybrid vibration observer also. So, in case of hybrid vibration observer, so both active and passive components are synthesized. These active, passive or hybrid dynamic vibration observers provide effective vibration control over a broadband frequency range when compared to passive and adaptive dynamic vibration observer. So, in case of the active vibration observer, structure become lighter, space and weight constraint will be there, it requires powers. So, when you are putting this active part, though we have to put the actuator. So, for that actuator we require power, applies a force directly into the system to dampen the vibration. There are several applications you can see. So, several applications are there. For example, so this Boeing Vitrol CS-47, where 5 active vibration observers are used. So, this is in aerospace applications. In also F-18 fighter plane wing with piezoelectric actuator for buffeting. Then in car suspension system also we can use this active vibration observer. So, active vibration observer reduction gears can be used also. These are used already, technical corporation program USA, Canada and Australia. So, then this RIVD J damper, then this sports car, in sports car also these things have been put. So, in bioengineering applications also you can see this vibration. So, this to control the vibration of the hand movement. So, this vibration bracket can be used, bracelet can be used. So, you can see this small video, you can see. So, you just see when he is taking the food. So, there is so due to this shaking of the hand, so it is difficult for him to take the food properly. So, to observe the shaking of the hand, so we can develop one bracelet, so that, or we can develop some vibration observer, so which will observe the vibration of the subject. So, similarly, there are several civil structure where this 634 meter tall Tokyo sky tree. So, Japan. So, here these tuned vibration observers have been used. So, then we have this tallest statue in the world, Statue of Unity, India. So, here also in the leg part you can see. So, 2 tuned mass damper systems are used here. So, it can prevent the vibration of the system. There are several literatures are available, and some of this literature, for example, you can see this Faram in 1911. So, this is US patent. So, here investigated 11 different models of undamped vibration observer to suppress the resonant vibration of the various primary system. So, these vibration observers are the passive vibration observer. The principle is simple. So, here, so in this case the secondary system. So, we are going to use a secondary system in the primary system. So, the secondary spring and mass are chosen in such way that, so the external excitation frequency will be equal to root over K2 by M2. So, similarly, this Krennic and Hosborg, so they developed this tuned mass observer in a flexible structure. So, it is published in 14 in JSP 2014. So, designed a tuned mass observer on flexible structure for vibration suppression of a single degree of freedom spring mass systems So, obtained fully balanced frequency curves by using fixed point theory optimization. So, proposed tuned mass observer applied to 10-story building, taut cable and on pedestrian bridge for attenuating vibration of the primary system. Similarly, this Jiang and Nishitani in 14 in their work, they optimum design for more effective tuned mass damper system and its application to base isolated buildings. They have designed non-traditional tuned mass damper. So, it is non-traditional tuned mass damper to suppress the vibration of seismic induced base isolated structural system. The optimal non-traditional tuned mass dampers suppress vibration in a wide broadband and required less tuned mass dampers stroke than the traditional TND. So, quasi fixed points theory of optimization is developed to obtain the optimal parameter for the observer. So, here you can see the structure. So, traditional mass damper. So, this is the traditional one and this is the non-traditional one. So, in traditional one you can see how the spring and dampers are used, and in case of the non-traditional one, so this is the primary M1 is the primary system. So, here the secondary system is directly connected to the ground. So, here the secondary system in case of the traditional, the secondary system is connected to the primary system, but in case of the non-traditional, the secondary system is connected to the ground itself. So, secondary spring and damper part can be directly connected to the ground. Let us see some active vibration type of observer. For example, so you can take the work of Villadal. So, Villadal in 19, so this is a recent paper 2019. So, analysis and design aspect of delayed resonator observer with position, velocity and acceleration feedback. So, we can give either the position, velocity or acceleration feedback, or a combination of all these three, or a combination of two of any two, either position velocity, position acceleration or velocity acceleration, position velocity. So, that way any combinations of these three can be taken and this observer can be designed. Here this is the primary mass. So, this is the primary system. So, in the primary system it is subjected to a force Ft and it has a displacement of xp, that is x primary. So, to that thing, the spring and damper, this is the passive part. In addition to passive, so a active part where ut is written. So, this is the active force is acting to the system. So, this active part is attached to or is connected this primary system and the secondary system. This analyzed lumped and distributed delayed resonator with acceleration velocity and position feedback. So, when we are using some feedback system, so there may be some time lag, and for that purpose, so one can consider a delay differential equation to write down this equation of motion. In that case, so one can use a delayed resonator to study the system. So, the proposed design criteria by comparing among various feedback and delay systems. So, then you can see this work of Kukera et al. In 2017. So, they extended the delayed resonator and design and experimental verification also carried out. So, they carried out design and experiment both delayed and non-delayed acceleration feedback control together with vibration suppression of the system. The operable frequency range is widened by including a non-delayed part to adjust virtually the mass and thus the natural frequency of the active observer. The properties and performance of the resulting algorithms are compared with the delay free proportional integral feedback control law. So, then this Brennan et al. Also in 2014. So, they investigated the simultaneous use of a resonator as an energy harvester and vibration observer. Previous class we studied regarding this energy harvester. So, we have seen, so in the parametric instability region, when the system response becomes parametrically unstable, so that time we can use them as a energy harvester, and here the opposite of energy harvesting will be the energy absorbing property. So, one can use the same system as an energy harvester or as an vibration observer depending on the range of frequency in which it is working, or depending on some other system parameters also. Changing the system parameter can control the vibration, and sometimes it can be used as a vibration observer or sometimes it can be used as the energy harvester. So, in this work they investigated and showed the use of auxiliary system to act as an vibration observer and an energy harvester simultaneously by providing broadband random excitation and single frequency excitation to the host structure. So, different optimizing criteria, namely Den-Hattok's equal peaks method, S2 norm of minimization of kinetic energy of the host structure are compared and studied. Here this is the host structure. So, in the host structure they have put the auxiliary system. So, you see the auxiliary system is connected to the primary system with a damper and a spring. So, spring and damper is used, and they have studied this system as both harvester and actuator, harvester and observer. So, there are several passive vibration observer where this nonlinear analysis also carried out. So, you can see some of them, for example, this work by Rabello et al. So, in 2019 they carried out this they analyzed the effects of time delay in the damping of the stability of the response of 2 degrees of freedom system, where the primary system is subjected to external harmonic excitation. Demonstrate that the time delay can act as a stability factor to control the vibration amplitude of the main system. They used this method of multiple scales to obtain the reduced equation for the primary and simultaneous resonance condition. Similarly, this Habib et al. They studied this nonlinear generalization of Den-Hattok's equal peak method. So, they obtained the optimum stiffness and damping formula for the nonlinear passive dynamic vibration observer attached to the nonlinear primary system, which shows Den-Hattok's equal peaks. So, in the frequency response curve. So, already we know, so when we are adding a secondary system to the primary system, so now we have a 2 degrees of freedom instead of a single degree of freedom system when we are considering only the primary system. As we have a 2 degrees of freedom system, so we have 2 natural frequency, and when we are adding the spring mass system, secondary spring mass system in such way that, so the natural frequency, the external frequency equal to root over k2 by m2. So, in that case, so at resonance conditions, that is when the external frequency equal to the first or the natural frequency of the primary system, at that position the response amplitude of the primary systems becomes 0. So, that means it is completely, the secondary system completely absorb the vibration, but though it is absorbing the vibration at omega equal to omega n of the primary system, but one can obtain 2 peaks near the 2 natural frequencies, 2 modal frequencies obtained in this case. As we have a 2 degrees of freedom system, so we have 2 natural frequency or 2 modal frequencies. So, when excitation frequency equal to these 2 modal frequencies, so that time now we are getting 2 peaks, but we are getting 0 response. So, equal to the 0 response when it is equal to the previous, the external frequency equals to the previous natural frequency of the system or the natural frequency of the primary system. Okay, that way is exactly what we are doing. So, by adding the extra spring mass system, so we are shifting the natural frequency or shifting the resonance frequency to the left and right of the original frequency, natural frequency of the primary system. That is why one can get 2 peaks in place of a single peak in case of a 2 degrees of freedom or this vibration observer case. So, there are several studies are also on this active vibration observer of nonlinear system. Many researchers they have also considered the nonlinear spring and damper in case of the secondary system also. For example, the Son and Zhu in 2016 they have developed a novel application of internal resonance in vibration suppression of an observer isolator combined structure with time delayed coupling control at the resonance frequency band. They have used method of multiple scales to obtain the reduced equations. So, vibration suppression effectiveness, control mechanism and stability of the steady state for different internal resonance conditions have been studied. They have used or they have considered 1:2 internal resonance. For 1:2 internal resonance, increasing time delay reduces the resonance peak about 40% and with 1:3 internal resonance condition. So, they have shown the resonance peak is reduced about 65% more than that of the 1:2 internal resonance. What is 1:2 internal resonance? If the second natural frequency or second modal frequency is 2 times the first modal frequency, we have this 1:2 internal resonance. Similarly, the second natural frequency or second modal frequency, if it is 3 times the first or primary frequency of the primary system, then it is 1:3 internal resonance condition. By adjusting or by taking different mass and spring in the secondary systems, we can generate either 1:2 or 1:3 internal resonance conditions, and by using these different internal resonance conditions, we can reduce the amplitude of vibration of the system. So, Lu et al. In 2018, so they have reviewed 296 recent articles on the state of the art technology for nonlinear dissipative device and observer. So, discussed various nonlinear vibration observer, namely nonlinear viscous damper, nonlinear energy sink, nonlinear dampers, particle impact damper, and characterized their wide frequency band of vibration attenuation and how to obtain high robustness in this type of analysis also has been discussed in the work of Lu et al. Here we can see now we can study the following systems. Now, you have seen the literature review, and from the literature review you can see that we have several type of, either we can have a passive vibration observer, we can have active vibration observer, or we can have this hybrid vibration observer. In this observer also we can have this internal resonance of 1:1. That means, when the actually 1:1 internal resonance is similar to this tuned vibration observer, where the natural frequency of the primary system equal to the excitation frequency, and it is also equal to the natural frequency of the secondary system. Natural frequency of the secondary system is root over k2 by m2. So, in that case we have seen this tuned vibration observer. Also, we can have this internal resonance of 1:2, internal resonance of 1:3 by arranging different spring mass damper system. Let us now consider, so let us now see how we can model this type of system, how we can analyze this type of systems, and what are the results and observations in this type of systems. So, when we are taking, let us take a piezoelectric stack actuator based active vibration observer. We can take several systems. So, in one case we can take both the primary and secondary systems to be linear. So, then we can take the primary system to be nonlinear, secondary system to be linear. Also, we can take the case when both primary and secondary systems are nonlinear. Similarly, the forcing conditions also we can change. So, we can have a single harmonic, or we can have multiple harmonic excitation present in this system. When we have these linear systems, so particularly one can find the response by applying this Laplace transform, or one may use this first order method of multiple scale also to study this system. So, one may study both primary and principal parametric resonance conditions, one may use this harmonic balance method also. So, a modified harmonic balance method will be shown here in this work, where by using that thing, so we can find the response of the system. So, we will study 2 or 3 different type of different systems in this work. Actually, this work is the PhD work of my student Mr. Sivanand Mahanti. So, he is working on this passive and active vibration observer. We can see this active nonlinear vibration observer with time delay. So, previous cases, so we have not studied the time delayed system. Here we are going to study the time delay system. So, active nonlinear vibration observer with time delay in acceleration feedback. We may use this velocity feedback and displacement feedback also. So, generally we will take a single degree of freedom spring mass damper system. So, we will see by applying this external harmonic and base excitation how we can obtain the Den-Hartog equal peaks. 3-4 systems we are going to study one by one. Let us see. So, let us see the first case. So, when we are going to study a piezoelectric stat actuator based active vibration observer. So, this is the primary system. So, in the primary system, so this M1 is the mass of the primary system, K1 is the spring, then C1 is the damping coefficient. So, it is subjected to the primary system is subjected to a force Ft and having this displacement x1 about the equilibrium position. We have added a spring K2, we have added a damper C2 and we have added a piezoelectric stack actuator having this property this KPE. So, that means when we are applying this voltage to the piezoelectric stack actuator, so it will behave as a actuator and it can be. So, if it is proportional, so we can take this force to be Kp into this displacement of this thing. So, in addition to the stack actuator, so we have added a spring. You just see a spring is added to the in addition to the stack actuator. So, this is the stack actuator. So, this part is the stack actuator. So, in the stack actuator we have attached a spring which can actually be useful. So, in case this piezoelectric stack actuator fails to work. So, here we will see by using this Laplace transform we will find the response, then the stability criteria in case of the linear system. So, you just see the system is linear system we have taken. So, by using this Routh-Hurwitz criteria we can study the stability, then we can see how we can use this optimization method to find the equal peak. Further we will use method of multiple scales and study the primary and principal parametric resonance conditions. So, let us see the mathematical modeling. So, mathematical modeling is simple. This is a 2 degrees of freedom system. So, either you can use this Newton's second law or this D'Alembert principle or this energy based method like the Lagrange principle and Hamilton principle to study or to find the equation of motion. In this particular case, one can conveniently use this Newton's second law to derive the equation of motion. So, for this purpose, so one can draw the free body diagram. For example, drawing the free body diagram of mass m1. So, if the spring is pulled upward, then it will exert a force K1 force downward and C1 x1 dot force in downward direction. So, as the mass is moving upward direction, then it will be subjected to a inertia force in the downward direction. So, inertia force equal to m1 x1 double dot. If one draw the to find the equation motion, so you can draw the free body diagram. So, now mass is moving upward. So, in that case this is K1 x1, K1 x1, then C1 x1 dot, K1 x1, C1 x1 dot, then this is m1 x1 double dot. So, this is the inertia force. So, in addition to these things, it is connected to mass m2 through the spring K2 and damper C2 and this piezoelectric actuator. For the spring K2, so we can have a force. So, the force will be in this direction. So, it will be K2 x1 minus x2. Similarly, we can have another force that is C2 x2 x1 dot minus x2 dot. So, in addition to that we have the force due to these piezoelectric actuators, force due to these piezoelectric actuator. So, the equation motion can be written, so in this form. So, it will be m1 x1 double dot plus k1 x1 plus c1 x1 dot plus k2 into x1 minus x2 plus c2 into x1 dot minus x2 dot minus or plus Fp equal to 0. Okay, so another force is also acting instead of 0. So, this will be equal to Ft. So, Ft is the force acting. So, Fp is the force given by the actuator, or Fa you can write also is the force by the actuator. So, total it will be equal to this. Similarly, so we can draw the free body diagram for the mass m2 and we can find the equation of motion. So, let us see what are the equation of motion we are getting here. So, we can give a displacement feedback of the primary system. So, acceleration feedback of the primary system and use this root stability criteria and use this fixed point theory of optimization. We have this nonlinear primary systems with the displacement and acceleration feedback. Approximate solution we have to do by using first order method of multiple scale. So, primary resonance and superharmonic resonance conditions we have to study. The nonlinear primary systems and observer with acceleration feedback further we will study. So, initially we will study this as a linear system, then we can make the spring to be nonlinear. So, when you are making this nonlinear, so one additional term will be added to the equation of motion. Further also we can take this K2 spring to be nonlinear also. So, a nonlinear term can also be added. So, further it can be more complicated by using multi-harmonic and parametric excitation to the system. So, primary resonance conditions and 1:1 internal resonance conditions may also be studied in this type of system. Slowly let us see. So, let us see the linear system analysis. So, in this linear system already I have shown how to derive this equation of motion and you have seen it is written in the same way. So, that is m1 x1 double dot plus k1 x1 plus k2 into x1 minus x2 plus c1 x1 dot plus c2 into x1 dot minus x2 dot equal to Ft minus Fc. So, this control force is written as Fc. This Ft force is acting downward and this Fc force is acting on the mass m1 by mass m2, this Fc. And this Fc, okay, for the second system also we can write this equation m2 x2 double dot plus k2. So, it is connected to the fast mass by k2 and c2 and then this k3 by the stack actuator. So, m2 is connected by the spring. So, this mass m1 and m2 are connected by the spring k3 and stack actuator kpe. So, that is why this for the free body diagram of m2 we can write this equation in this form, that is m2 x2 double dot plus k2 into x2 minus x1 plus c2 into x2 dot minus x1 dot equal to Fc. So, now this Fc, so if we are taking only proportional type of controller, then we can write this equal to kr into x1 plus delta 0 minus x2, where delta 0 is the initial displacement of the stack actuator. So, minus x2 here kr. So, as we are using kr can be written. So, if we are writing the stiffness of the actuator equal to kp and k3 is also a spring. So, the stiffness of the actuator we have taken kpe and so this k3. So, both of them are in series. So, the equivalent stiffness can be written as kr equal to kpe into k3 by kpe plus k3. So, that is why this Fc can be written as kr into x1 plus delta 0 minus x2. So, this way we obtain two equation motion and then so from this equation motion, so we can write by non-dimensional form also we can write. To write it in non-dimensional form, so first we can divide this m1 everywhere, m1 in first equation, or m1 by dividing m1, this equation becomes x1 double dot plus k1 by omega 1, k1 by omega 1, now it becomes k1 by omega 1 equal to omega 1 square or k1 by omega 1 root over is taken to be omega 0 in this case, then k2 by m1, c1 by m1, c2 by m1. So, m1 is initially divided. Now, by taking a time non-dimensional time one can take tau equal to omega 0 t. For example, you just see only these two term, let me derive and show you. So, m1 x1 double dot plus k1 x1. So, first you divide this by m1. So, this becomes x1 double dot plus omega 0 square x1 as omega 0 square equal to k1 by m1. So, now taking tau, this non-dimensional time equal to omega 0 into t, omega 0 is radian per second, time is in second, second cancel. So, this becomes radian which is non-dimensional. So, by taking tau equal to omega 0 t, so this x double dot which is differentiation with respect to time t. So, we can write this equal to, so d square x1 by d tau square. So, it will be omega 0 square will be multiplied with this thing, because twice if you are differentiating with respect to, so this is d square. So, d square x1 by d t square will be nothing but it will be omega 0 square d square x1 by d tau square. So, this omega square you can take, this omega 0 square can be taken common. So, this becomes x1. So, this into omega 0 square, yes or no. So, this term will be there and it will be equal to 0. So, now you can divide, as omega 0 is not 0. So, you can divide this term and you can get this as the equation motion. So, here you just note the coefficient of d square x1 by d tau square is 1, and also the coefficient of x1 is also 1, which is shown in this equation and in the second equation also. Second equation you just see. So, first equation you got in this way. So, by taking this tau equal to omega 0 t, and you have used this non-dimensional parameter and you have written down this equation. Similarly, we know that we can write the c by m equal to 2 zeta omega 0 as omega 0 is. So, that way you can write. Then we can use this non-dimensional parameter. For example, let us use x1 equal to capital X1 equal to x1 by x0, capital X2 equal to x2 by x0, x equal to capital X2 minus capital X1, k equal to kr by k1, mu equal to mass ratio mu2 by mu1, and v equal to v by v0. Omega 0 already you have taken equal to root over k1 by m1, and omega 2 equal to k2 plus kr by m2, and this external forcing frequency omega 2 equal to omega 2 by omega 0. Also we can consider some other terms like lambda equal to n d33 v0 by x0. So, this is due to that piezoelectric stack actuator, and zeta 2 equal to c2 by 2 m2 omega 2, and zeta 1 equal to c1 by 2 omega 1 omega 0. So, by writing this way we can have these two equation. Using these two equations, so these are, you just see, initially we are finding for the linear case, then we will consider the nonlinear case. So, if you take the Laplace transform, so taking the Laplace transform, the equation becomes s square plus 2 zeta p s plus 1 into z p s minus mu z s square plus 2 zeta a mu z a s into z s equal to f s minus k lambda v s, and second equation becomes s square plus 2 zeta a omega a s plus omega a square into z s plus s square z p s equal to k lambda v s by mu. This way you can derive this equation of motion. So, let us see the previous slide. Here you just check, after writing this taking the Laplace, we can take different type of feedback loop also, and we can study the system. So, if we are taking this acceleration feedback of the primary system, we can take acceleration as acceleration equal to x double dot. If the displacement is x, acceleration is x double dot. So, we can write, so in this feedback case, that will be equal to, that forcing term will be equal to minus kc x1 double dot. So, the transfer function of the primary mass is obtained as Gs equal to x1 s by Fs. So, in that case it will be equal to a square plus 2 zeta 2 omega 2 s plus omega 2 square plus b 4 s fourth plus b 3 s cube plus b 2 s square plus b 1 s plus b 0, where the coefficient b 4, b 3, b 2, b 1 and b 0 are expressed as, you can express in this way. So, these are given how you can express these coefficients. So, this is the control block diagram for the acceleration feedback of the primary system. This Ft is applied to the system. So, we have a primary system, sensor, feedback. So, sensor, so we are getting the acceleration. Actually, you know that it is easier to get the acceleration by putting a accelerometer on the vibrating system. So, by putting the accelerometer we can sense the acceleration and that thing can be used effectively as the feedback, and getting that feedback we can control the vibration of the system. Now, the passive part of the vibration, observer is first optimized according to the standard procedure, and accordingly the observer frequency and damping parameters are set as omega 2 equal to 1 by 1 plus mu and zeta 2 equal to root over 3 mu by 8 into 1 plus mu. So, using this optimal tuning ratio, so damping ratio, the stability of the system is studied by Routh stability criteria. As we have this S0, S1, S2, S3 and S to the power 4. So, we can write down this coefficient. After writing this coefficient, then we can check the first column of the, we can construct the this Routh array. So, from this Routh array, so you just see we have this fourth order equation. So, this fourth order equation can be written conveniently. So, after writing this fourth order equation, so we can write the coefficient then of S4, then S2, S3, S2, S1 and S0. So, the first column will tell, so if there is a change in the sign, then we can tell the stability will change. From this thing, so we can see that Gj omega will be equal to omega 2 square minus omega square plus J2 zeta 2 omega capital omega 2 omega divided by b fourth omega fourth minus b square omega square plus b 0 plus j b 1 omega minus b 3 omega cube. So, now one can plot this omega versus this Gj omega. So, this is similar to the magnification factor versus this omega or the response amplitude versus omega. So, you can easily observe that by using that thing, when there is no feedback. So, you can see the system will be, so system will, the primary system will have a resonance condition. So, now for the secondary system, so now by taking these parameters, so one can plot it, and for 3 different value of alpha. So, alpha equal to 0, alpha equal to 0.1 and alpha equal to 0.3, one can plot this omega versus Gj omega, and clearly one can observe for alpha equal to 0. So, we have 2 peak and the response amplitude is very high. For alpha equal to 0.1, by taking alpha equal to 0.1, so now it is reduced, and but at omega equal to omega 1, still it is not equal to 0. So, here also still it is not equal to 0 or it is not reduced. By taking this alpha equal to 0.3, so you can see the response amplitude at omega equal to 1, so is reduced very much. So, omega equal to 1 is nothing but, so this omega is the frequency ratio. So, that means when the external frequency equal to the natural frequency of the system. So, previously we have seen, so from the primary system it tends to infinite, but by adding the spring mass system in a proper way, you can see that it can be reduced considerably. So, one can plot this area versus area to find this optimal value of alpha. So, here the optimal value of alpha is obtained to be 0.19. So, variation of area under frequency response curve with different value of alpha. So, at any damping, instead of if we are taking or when you are plotting this frequency ratio versus g j omega. So, we can see, you can see irrespective of damping. So, for this curve is plotted for 3 different value of zeta, that is the damping ratio. So, in that case you just see irrespective of damping. So, there are 2 points, that is omega A and omega B, about which all the curves pass. One can note these 2 points. So, at any damping ratio the frequency must pass through these 2 fixed points for the optimal condition. So, this omega 4th minus 2 omega 2 square into 1 plus mu plus 2 by 2 plus mu minus alpha omega square plus 2 omega 2 square by 2 plus mu minus alpha equal to 0, and we can have this omega A square and omega B square by solving this equation. So, we can get 2 value of omega. So, this is the characteristic equation. From the characteristic equation we can get these 2 value of omega, for which this will satisfy this equation. So, this is omega A square and omega B square will be equal to omega A square into 1 plus mu plus 2 by 2 plus mu minus alpha. So, this is a quadratic equation in omega square. If you take omega square equal to A, then this equation becomes A square minus B, or if you take omega square equal to x. So, this becomes x square minus A B x plus c equal to 0. So, this is a quadratic equation in omega square. You can find the root of this quadratic equation by using this formula. So, that is minus b plus minus root over b square minus 4ac by 2a. So, using that thing, so you can get this equation. So, you can observe the value of this omega a and omega b, and from this thing, so you can get these 2 points where this these 2 fixed point. The amplitude of the frequency corresponding to omega a and omega b can be written as g omega equal to 1 by 1 minus 1 plus mu into omega a square and 1 by 1 minus 1 plus mu into omega b square. So, substituting the above equation, tuning frequency leading to the same response amplitude at the fixed point may be written as g omega a equal to g omega b, that will be equal to root over 2 plus mu minus alpha by alpha plus mu, and as these 2 points are fixed points. So, if you differentiate this thing with respect to omega square. So, del by del omega square g omega square omega equal to omega a will be equal to del by del omega square g omega square omega equal to omega b must be equal to 0. So, the optimum tuning ratio omega 2 can be obtained in this way. So, this is the optimum tuning ratio omega 2 equal to root over 1 minus alpha by 1 plus mu whole square. So, this way by applying this, so using this optimal tuning ratio, damping ratio by Routh stability criteria, the system can be said to be stable for 0 less than alpha less than 1. Similarly, one can study the displacement feedback of the primary system. So, in case of displacement feedback, so it can be taken as V equal to minus Kc into x1. So, in that case this Gs term can be written in this form, that is x1 by s by Fs equal to s square plus 2 zeta 2 omega 2s plus omega 2 square by a4s4 plus a3s cube plus a2s square plus a1s plus a0, where the coefficient a4, a3, a2, a1 and a0 are expressed as. So, this is the expressions for all these parameter. So, the optimum tuning ratio and damping ratio can be obtained in the previous way, that is omega 2 will be equal to 2 plus alpha into 1 plus mu by 2 into 1 plus mu square, and zeta 2 equal to root over 6 mu minus alpha into mu square plus 7 mu plus 6 divided by 16 into 1 plus mu into 1 plus alpha mu. So, using Routh stability criteria, the value of stability region for the control gain can be obtained as minus 1 by mu plus 1 less than alpha less than mu by mu plus 1. This way one can study the system previously we have taken the systems to be linear. So, now one can take the nonlinear systems also. So, in this case the equation, so now we have added a nonlinear term, that is q x1 cube here we have added. So, we have taken the nonlinearity in the primary system, and the system is subjected to a forcing f tau cos omega tau. So, as we have taken the nonlinearity in the primary system, so this equation can be written in this form. So, now in that case, so what we can do, so here we can order the equation, we can order them by using the order of epsilon. So, actually while taking this order of epsilon, you must know the relative magnitude of each term by assuming that the cubic nonlinear is of the order of epsilon, and the forcing is also of the order of epsilon, and the damping is also of the order of epsilon. The equation can be written in this form. So, the equation can be written x1 double dot plus omega 0 square x1 plus epsilon z1 x1 dot plus epsilon q1 x1 q minus epsilon z1 x2 dot minus epsilon square r x2 equal to epsilon f tau cos omega tau, and second equation equal to x2 double dot plus omega 2 square x2 plus z2 x2 dot minus z2 x1 dot equal to 1 by epsilon v x1. So, for ordering the equation, the following values are taken. So, these are the values taken. So, from here, so one can obtain this omega 2 and this zeta 2 and z2 also. So, this way the equation you can write by taking the nonlinearity in the primary system. So, if you want to take the nonlinearity in both primary and secondary system, so the equation can be modified. So, you just see this is the term nonlinear term added to the secondary system. So, if you are taking this one, so one can add the cubic nonlinear term and quadratic nonlinear term. The equation will be m2 x2 double dot plus k2 into x2 minus x1 plus k21 x2 minus x1 square plus k23 into x2 minus x1 cube plus c2 into x2 dot minus x1 dot plus c21 into x2 dot minus x1 dot square equal to fc1. Similarly, for the primary system, so it will be m1 x1 double dot plus k1 x1 plus k12 x1 square plus k13 x1 cube plus k2 into x1 minus x2 plus k21 into x1 minus x2 whole square plus k23 into x1 minus x2 whole cube plus c1 into x1 dash plus c12 into c12 into x1 c1 into x1 dot. So, it will be c1 into x1 dot not dash dot c12 into x1 dot square plus c2 into x1 dot minus x2 dot c21 into x1 dot minus c2 x2 dot square. So, you are taking the nonlinear damping also. So, it depends how you are defining your nonlinearity in damping and in the spring. So, depending on that thing you can write down this equation of motion. So, by taking all the forces acting in the system, today class you have learned how we have derived this equation motion for different vibration observer system, and also you have seen how we can obtain these equal peaks, or we can obtain two fixed point at which irrespective of damping all the observers will have the same value. Next class we will see how we can solve these equations and we can obtain effectively, or we can have the effective vibration observer in case of the nonlinear systems. Thank you.